Okay, so it's going to be a really packed lecture. I'm probably not going to be able to teach you effectively today because it's a very dense, right? So today is just an introduction to what you're ultimately going to have to go home and read more about, right? Because I'm not going to be able to flesh it out nearly fast enough, right? But this is basically going to be true from now for the rest of this semester, right? You are to take these classes as me showing you the stuff that you need to go home and learn. Right? I'm just trying to give you a first exposure to it, right? Because it's not going to be possible for me anymore to like teach you in such a way that you leave here and are able to do it. So don't feel bad if you don't understand anything. You have to go home and read again. Okay, so I'm missing my page 1, so I'm just going to make it up. Let's see. What are we supposed to do today? What was the title? Does anyone know the title of today's lecture? Let me make it up. I think it was something like differential rules. So what did we learn yesterday? Does anyone recall?
We learned about the definition of the derivative.
We learned about the definition of the derivative, but what kind of definition did we establish?
First principle.
First principles, but...
Through tangent lines.
Okay, sure, I'll accept that. We established a geometric type of description of the tangent line, right? So from yesterday, we have, or recall, have f prime at x is equal to f of x plus h. Oh, even I forgot to write the limit. Right. Limit of h goes to 0 of f of x plus h minus f of x over h. Right? This will give us the slope of the tangent line at the point x on f. Right? However, and also recall that we had this funny differential operator, which was a mapping which takes functions and maps them to their derivative. Okay, so for this lecture only, I'm going to draw a distinction between this piece of notation and this piece of notation. And then after this lecture, we're just going to interchange them. So the reason I'm distinguishing in this lecture is because this really is a geometric definition, right? This is a definition about being on a plot and following points on a graph. This is basically an algebraic definition, right? It's a function, and it says, okay, I'm a function, give me f, a function, and I'll return to you the function of its derivative, right? So today, we don't want to take derivatives using limits, okay? We want instead to establish some rules that we can use. Okay, good news about differentiation. All you need to do is practice. There's really not much conceptual understanding required for you to mechanically do derivatives. So you just need to do like 1,000 of them. So I'm going to give you a series of rules today, which are mostly enough to be able to differentiate anything. Most of you have already probably seen the rules, maybe from high school or in an earlier attempt at this course. But what we have to understand is that at this point, if I asked you to do this question, what is the derivative of x squared? Why? But why? Why should bringing down the exponent and multiplying in front be a rule for giving us the tangent? Right? You're correct, but have you thought about this? Why on earth does this process of like taking down the exponent and multiplying and reducing by 1 end up providing us the slope of the tangent? That's kind of a weird coincidence, but so be it. Okay, so we know that this is equal to 2x, but technically speaking, I would have to prove this. Now, let's look at this then. Here's a proposition, which means it's going to be something I'm going to write that I suspect to be true, and we're going to have to give some type of evidence. Wouldn't it be nice if we could establish a rule that said this? The derivative of x to the power of n is equal to n times x to the n minus 1. Okay? That's precisely the rule we used here. Right? We took 2, we put it down, and then in the exponent we had a 2 minus 1. You recognize this rule, right? I think this is called the power rule. How would you think we could go about establishing that this is true? You took it for granted from your high school teachers. or maybe even from your professors. Everything you need to know about answering this question is on the board. So when you get stuck, one thing that you should try doing is just applying the definitions that you were given. Yes, sir?
If I try to take the antiderivative, the second one?
You're going to introduce antiderivatives? We haven't even established the notion of derivative fully. Okay, let's get to the complicated stuff when it's absolutely necessary. For now, let's stick to easier stuff. All you have is this definition. You're stuck. You have to use this. So let's see what happens. Right, so we're going to write a proof. You don't really have to provide proofs. Proofs are just basically like doing calculations, not using fixed numbers. So there really isn't any difference between using the number a or using the number 7. They're treated exactly the same. Okay, so how can I prove this is equal to this? Well, I know that this, d by dx of xn, is equal to what? By definition. To the limit definition of the slope, right? So this is going to be limit h goes to 0 of x plus h to the n minus x to the n over h. Correct? Any mistakes? No, this is just a basic definition. Well, I'm just use the definition of the limit once, precisely as it's written on the board. Now, let's try to expand this. Okay, I want to expand this. How would you expand it? Or what would we write in our problem-solving framework at this point? Well, can you expand x plus h to the n? I doubt it. Name some of the words from the problem-solving framework. We're stuck. Why are we stuck? We can't expand x plus h to the n, right? Okay, so I'm going to give you two arguments here, right? We need to work with this equation. So I'm going to show you something cool that you may not know about, which you don't need to know. And then I'm going to give you another explanation that you can understand just basically using pre-calculus. But there's this thing called the binomial theorem. You don't need to know it, but it's cool. Binomial theorem. And we're going to borrow a little piece of technology from a branch of mathematics called combinatorics, which is the mathematics of counting stuff, essentially. And in that discipline, they have something called, have you ever seen this? The binomial, I think this is called choosing. I actually forget what this is called. But anyways, this is a piece of notation that's equal to the number of ways you can choose, choose k objects from n objects. Right. We need mathematics to say if you have 7 balls, how many groups can you make if you choose 3 balls from those balls? Right? You labeled them 1 to 7. It turns out there's this many, which actually, you guys know what a factorial is? Okay, this is going to be n factorial over n minus k, k factorial. N minus k factorial, k factorial. You don't need to know this. Right? Why am I telling you this? Well, the binomial theorem says this. X plus y to the power of n is equal to. Now, do you realize that when you do stuff like this, what's the degree of this term? What's the degree of this term? No. 1 and 1. 2. What's the degree of this term? 2. So what are the degrees of all the terms? Okay. The same is going to be true for here. When you expand this totally, every term is going to have degree equal to n. Right? So for instance, the first term should be easy to pull out. What should the first term be? X to the n. What should the last term be? Y to the n. Okay, so what are the in-between terms? Well, okay, so this really is x plus y multiplied against itself n times. Right, so how many terms are we going to find with n minus 1 many x's and exactly 1 y? Right, that means for n of these, you just choose 1 each. So you end up getting n many terms like this. Right? and then more. Now, so each of the terms is going to have a number in front of it, right? So like the first one was easy, it's a 1. The last one, it's easy as a 1. This one's more difficult because you have to expand and collect terms. It turns out the generalized expansion of this looks like this. The first term is n many objects, choose n of them, x to the n, y to the 0, plus n objects, choose n minus 1 of them, x to the n minus 1, y to the 1, plus n objects, choose n minus 2 of them, xn minus 2, y squared. Finally, the very last term is going to be n choose 1, x to the 1, y to the n minus 1, plus y to the n. Don't freak out too much. I'm just showing you this sort of as like this neat tool. If you've ever seen Pascal's triangle, you can get this out of Pascal's triangle. But we do have a way to take equations like this and to give the expansion. And why do I want this? Well, we're going to have to evaluate this limit and hopefully cancel out a bunch of h's. Okay, so this is going to be the expansion. So I'm going to erase this because I want to keep that, and this is less important. So let me just erase this. Okay. Okay, so let's take that and continue. So we have this is equal to the limit of h goes to 0, and I'm going to now write an expansion for that x plus h to the n. So the first thing is going to be x to the n. The next thing is going to be n, x to the n minus 1, y, h. The next thing is going to be n choose n minus 2 objects, xn minus 2, h squared. And then we're going to continue all the way down to hn. Then we have, so that's the x plus h to the n. Then we subtract an xn. And then all of this, Jesus Murphy, is over h. Okay, so let's look at this, right? I haven't really done anything too complicated. I just said, look, I know that there's a way that I can expand that x plus h to the n. Now, what's this? xn. What's this? Minus x to the power of n. So I'm not going to keep rewriting this over and over and over again. So please pay attention, because I'm just going to do cancellations like that. I'm going to cancel this. Okay? In the notes, I did it like line after line. So you can get those notes. What's the next thing that I can cancel? Well, what are we always trying to do in these limit calculations? Right, we're dividing by an h that's 0. In all of these calculations, we're trying to get rid of that h. Yeah? Exactly correct. And can we do that?
Oh, I was gonna ask if we could cancel the h over there with the h. Like one of the h's at the top, or we can't do that?
We can do it, but not with one of them. With all of them. Okay, so provided that the top, we can factor out an h, we can get rid of this one on the bottom. Is it true that we can factor out an h from the top? Yeah, look, the only things without h's got canceled somehow. Okay, so we can remove one of these h's now from the top. Okay, so I'm going to do this. That h is gone. I got to reduce this h by 1. That's totally easy. This one has to be reduced by 1. And this one has to be reduced by 1, so it just goes away. Okay, so now we're left with this. Okay, are we now able to take h to 0? Is there anything preventing us? Okay, so what is left over? Yes, sir?
The very first thing.
Only this. nx n minus 1 plus, well, who cares what this is? There's an h, and it's 0. So that disappears. Every term in here is going to have at least one h. This is going to have the most, h to the power of n minus 1. But the point is everything here has an h. Savvy? What are we left with? This. What have we discovered? Power rule. Right? We've discovered that the derivative of x to the power of n is equal to n times x to the power of n minus 1, provided n is greater than 0 and it's a natural number. Okay, this is why you have power rule. This is why x squared derives to 2x, because that's what it derives to. Based on our geometric definition of the derivative, this is algebraically what falls out of it. So now, strictly speaking, it would be dumb to ever use a limit calculation to find one of these. We found all of them, and they're always going to look like this. So the first rule of differentiation is the power rule. The derivative of something, x to the power of n, where x is the indeterminate, is equal to n times x to the n minus 1. Right? We pull this down. Now, our proof assumed that n was a natural number. It is actually possible to demonstrate this for n any real number, whether it be negative, a fraction, pi. I can't show you this proof. It's too complicated. But suffice it to say, I believe most of you would be able to understand it after some study. But it's not really that useful in our course. Okay, so let's do some examples, just to see what you guys have absorbed. And these aren't going to be trick questions, okay? We're not trying to trick you. D of x cubed over d of x, what is it?
3x squared.
Yeah, 3x, 3 minus 1, which is 3x squared. Okay, what about dx? Oh. D, what am I doing? Oh. X, yes, miss.
I'm just trying to understand how come you wrote it that way instead of maybe putting it in brackets.
Putting what in brackets?
X cubed in brackets?
This one?
Yeah, I'm trying to understand why you wrote it that way.
Well, this is just a piece of notation saying, like, so you could do it two ways. You could do it like this, right? So if we put something out in front, you usually have to say, this is what I want the derivative of. But when I put it in the denominator like this, it's just sort of like the brackets are like implicitly associated with that function.
Okay, and so is it written this way on the test? Like in that?
You'll have to be comfortable with all ways of it writing. None of this is ambiguous. Everything has precisely one meaning. You can write it in whatever way you choose, but I don't see a difference between like the left and the right. Neither should you, right? Some things are contextual.
Right, I'm just saying that I'm not familiar with that way, like you writing it that way, but I haven't seen it written that way before.
Well, how would you normally write it? With a bracket?
The way that I had seen the professor write it would be like d over dx and then bracket the function.
Like this?
Yeah.
Yeah, go do that if you want, but they're redundant brackets, right?
No, but what I'm saying is it's the understanding, right? Like like if it's written that way, like where I probably would get confused, like if I'm not familiar with certain ways that like it's written, I would get confused on a test. Like what is it? What's being?
Well, it's going to be all of them. I'm telling you, you have to be comfortable with all types of notation. I can't change your textbook or like the way that we write math. Like, I'm sorry that your like other professor and teacher taught it to you like this, but it's just it's a fact that all mathematicians will interchange these pieces of notation. You got to be comfortable with it. That's how we're going to write. All right. We have to follow notation. I didn't invent it. You can always do this, but like this and that are equivalent.
I understand.
Yeah. I'm going to dump this notation after today pretty much anyways. I prefer the prime notation, so it's not even going to be that much of an issue. Yeah. Okay, so let's do dx to the root 2 over dx. What about this one? Yes?
1 over 2 root x.
1 over 2 root x? Oh, you rationalized it.
Can I not do that?
Yeah, you can, but it's less clear. I'm just going to do this. Easier. You did an extra step? Yeah, sure. That's probably better. Don't we want the rationals in the numerator?
Yeah.
Okay, so that should be fine. Okay, last one. All right, I was right in here. Okay, I'm out of room. I'll write it here. D of cx to the power of 7 dx. What is it? Yes, miss.
7c x to the power of 6
No.
plus
No. I'm tricking you. What rule are you using for this?
product
We don't have product rule.
power
We have power rule, but that doesn't include constants.
So you take the constant inside.
Then you need product rule.
Yeah, so C.
We don't have product rule yet.
I
You may have product rule, but I'm developing this as if we haven't seen it before. What I'm trying to establish is like, I don't have a rule for this yet. Like the next thing I'm going to do is develop the rule for this. Right? I'm not sure. No, I'm trying to demonstrate. Don't bring in other math, right? You have to remember, we only have the tools that we established. So this was deliberately a trick question. So don't feel bad. At least you attempted to answer. Pardon me?
Did you say no trick question? Did you say no trick question?
That was a trick question. That was a trick statement. I'm a tricky bitch. That's how you have to treat every question on the midterm, as if we're trying to trick you. When I say I'm not going to trick you, you should be deeply suspicious, right? Okay, another trick question. What about this? We can't do it. Why not?
Because we haven't developed anything to.
We don't have a rule for adding sums. Right, so the next sensible thing to do would be, because remember our goal is to like eliminate the requirement of doing limits when doing derivatives. We want to do something that's way faster, like just apply a bunch of rules. So we have a rule on one of these guys. The next smart thing would be to develop a rule for working over sums. So here's the sum rule. And the sum rule is written like this. So the derivative of f plus g is equal to the derivative of f plus the derivative of g. All right, proof. I'm going to omit this because I don't have much time, but you could do it. Like this proof isn't outside the scope of your abilities. You have enough tools to like demonstrate it. All you'd have to do is like add those limits together and you could work it out. Okay, so let's return to that example. So then what is it the case? What is d dx of x to the 2/3 plus x squared? That's going to be d dx by x to the 2/3 plus d dx x squared by some rule. And then we get 2/3 x to the 2/3 minus 1, which is minus 1/3, plus 2 to the x to the 2 minus 1, which is 1, by power law. I'm not expecting you to write these when you do these. In fact, please don't. I want you to be able to do derivatives as fast as you can. I'm just being very explicit today. Over the course of the lecture, I'm going to start giving less and less details about the expansion. Okay, so what about now that cx squared? Do you think we can get it? I want you guys to start thinking like a mathematician. Okay, so recall this one. We don't know yet what this is. dxc x to the power of n. Does anyone have any idea how we can use the rule we just established to get a rule for this one? Yes, miss?
We take the c out, so c d over dx, x to the power of n.
Okay.
And we just do power rule.
But that's what I'm trying to prove. That we can bring c out. Right? That has to be demonstrated. Yeah.
Well, multiplication is just addition.
Multiplication is just addition. So what is this really?
So it's x to the n plus x to the n plus x to the n c times.
Does everyone follow that? Okay, but we're done now, right? Because then this is this. By some rule. And then we get c d dx x to the n. There you go. So now we know how to do this, right? By using a rule that we developed before to get a new rule. This is the nature of mathematics. We have rules, and we're like putting them together to make new rules. It's like building this giant machine. Okay. So you know how I keep bringing up polynomials? Polynomials are great because it turns out they're continuous everywhere, they're differentiable everywhere in their domain. They're smooth, they're just basically like functions that are easy to work with. We always prefer working with polynomials. If I asked you to take a derivative of a polynomial now, how would you do it? You go to the geometric definition and start running limits?
No.
What I want you to notice is, notice, we have enough rules to differentiate arbitrary polynomials. So recall a polynomial looks like this. It's some real constant, x to the power of n, and then another one, drop the degree, all the way down to this. Okay, so this is an arbitrary polynomial. If I take the derivative of this, can I do it? Do I have enough rules for this? Yes. You take this, you break it up over the sum, you apply the differential operator to each of these terms individually, and I just told you how to take derivatives of, well, what are technically called terms. Right? So at this point, it is no longer necessary to use the limit definition in order to take derivatives of polynomials. Right? Because we know how to do it algebraically. Right? Doing those limit calculations were cumbersome. So that's why we did it once. We did like a super rule, and we're just going to say, okay, yeah, it's justified. It's justified for us to make these type of simplifications. So just for an example, what is the derivative of arbitrary polynomial? 3x squared minus 2x plus 1. Give her a go while I wipe down the board. You see that? Murphy. Ah. Anyone have an answer? Yes, miss. 6x minus 2. So I hope everyone, that 1 is technically 1 times x to the power of 0. So just note, I guess we have, I should have given you this as a rule, but derivative of c such that c is just a constant number is 0. We actually don't need that one because of the power rule. Okay, so let's try something else. So I would never ask you on a midterm or test or final, take the derivative of that polynomial. That's far too easy of a question. That's a mechanics question, boring. What I would ask you instead is something like this. Where does y equal x to the 4 minus 2x squared plus 2 have horizontal tangents? Could you do this one? Okay, so what do we have to do? Yes, sir?
We have to find where the slope equals 0.
Slope of the what?
Slope of the tangent.
Okay, perfect, right? So the first thing I want you to do normally is rephrase the question at least one other way. Right? If you're able to rephrase the question at least one other way, that's a good indication you probably understand what the question is asking. Suffice it to say, the first step to solving a question is to understand the question. That's deeply important, actually. Okay, so basically the equivalent question find x in the domain of y such that the tangent slope is 0, by which I really mean find x in the domain of y such that, what's the algebraic way of describing this? Yes? Yes? Is what? Equal to 0. The derivative of y has to be equal to 0. Okay, this is what we're looking for. Okay, so notice, this question is asking you basically take the derivative of a polynomial. So I will ask you to do things like take a derivative of a polynomial. I'm just not going to ask you it that straightforward. Right? I'm going to ask you a different question. A question that is ultimately going to force you to take the derivative of a polynomial, but I want you to know why you're doing it. Right? In this case, you're doing it to find out some information, not because we're trying to exercise you mechanically. Right? So it's normally the case that we're going to be asking you to do something pretty straightforward. It's just sort of hidden behind a question. So I guess it is very useful to rewrite the question. Okay, so now all we have to do is actually do it. Right, so dy over dx is what? 4x, 4 minus 1, 3, minus 2 times 2. Whoops. That's 4x squared. 1 plus 0. Don't write the plus 0. I'm just doing it right now to emphasize that it disappeared. Okay, so where is this equal to 0? Right, so this is equal to 0 when 4x cubed minus 4x is equal to 0. Okay, so I just remove an x.
4x.
And a 4.
I remove a 4x. Okay, so I get 0 is equal to x squared minus 1. You told me to remove a 4x.
Factor it
4x is x squared minus 1.
out. And then you can expand in the middle.
This is 4x, x plus 1, x minus 1. So what are the solutions?
X equals 0 plus minus 1.
Damn it. You guys are too smart for me today. I was trying to trick you. Okay, so in my notes, so what I was hoping you would do is divide by x here. Right, that'd be something very normal to just clear out the 4x, because there's a 0 on both sides. Well, I could have gone from here and I could have taken this and divided both sides by 4x, right? Which is what I thought most people would do. But the problem is that x is a 0, there's 0 solution. So when I divided by x, I was actually dividing by 0. So I wanted to have a good point about being careful when you're doing this, but you did it properly. So when you're trying to find solutions, don't divide by stuff. It's factoring that you want to do. Factoring will save all the solutions. Dividing will get rid of them. And sometimes you divide by stuff that you're not supposed to. Yes, sir?
I have a question. So if I was on a test and I were to mess up the calculations, but I know what rule to use, if I state the rule, would I get partial marks for that?
No. No. It's like I'm saying, can you please multiply these two numbers? And you're like, I don't know how, but I know I have to multiply. It's like, no, yeah. It depends on, if I was testing you on something very, very, very complicated and you made a genuine error in some mechanics, then fine. But if I'm you need to be able to take a derivative, right? It's not good enough that you know that there are rules. You really have to be able to take derivatives. And the only way to gain competency is to practice. You need to do 300 of them. Right? It's just something mechanical. It's like learning how to multiply or divide. There's really not much thought that goes into it. You just have to be very careful. Yes, miss?
For the one up there, for the example, we said it was 6x minus 2. Can we leave it like that, or do we have to also factor out the 2?
Oh, no, you don't factor out. That's fine.
We can just leave it.
As long as your answer is equivalent to the final solution, that's fine. Right? There's this notion that you can't really, there's something called canonical form. Right, which means that I want the one answer. I want everything to look exactly the same. But it's well, 1 over root 2 is 2 root 2 over 2. Like they're the same thing, but they're written differently. So I can't really insist. I can't write down a bunch of rules that would make it so all of you are giving me back the exact same number each time. The only way to do that would be for me to give you a calculator and say, hey, at the end, just calculate your answer to a few decimals. And you should get like 1.286. Yes, miss?
I just want to clarify like the notation. So find x and then e.
In the domain of y,
Okay, domain of y and then s dot.
such that,
Okay.
sorry, yeah,
S. So is that a s dot t dot?
such that, yeah.
Okay.
It's sorry, it's just an abbreviation. Yeah. Yeah, stop me if I ever use a piece of notation that I haven't introduced, because I've done this so many times I forget what I've shown and what I've not. Yeah, it just means such that. It's, yeah, find this under the constraints of this, basically.
So like on a test, it may be written like that.
Oh, no, we're not, if on a test, I'll write everything out in full.
In full English.
Full, yeah, well, I'm going to use notation as well. You have to be able to use notation, right? If I say, take this, you have to be able to know what that means.
I understand that.
Yeah. Okay. Okay. This is the new board, yeah? That's the old board? Yeah. But that's half the trouble, is fighting with the notation. And that's why math is scary. So we introduce all these new symbols, and they're really not overly complicated, but if we had to do everything with English, these boards would be full of English. Like, every inch of this would be covered with words. What time is it?
11:54.
55.
I have an hour, yeah? Okay, not 5 minutes. Okay, so maybe. Okay, what other rules do you want? So I'll motivate it again. How about. Whoops, I skipped a rule. Product would be a good place to start. Division's a little bit more difficult than multiplication usually. But there's one more thing I want to indicate to you, and I'm not going to prove it. This d dx of, remember this guy, the natural base, the natural exponential function? Does anyone know what this derivative is? No? This is kind of a weird function. Its derivative is itself. Okay, so I could prove this. You would understand. It would take me an hour. So I'm not going to do it, right? So I'm going to omit this. But I'm omitting it not because it's too difficult, but because I don't have enough time. Okay, so to motivate the next rule that we want, let's do this. How can we do something like this? How about x squared e to the x prime? Or I guess I shouldn't use that. I guess I should say this. Can we do this?
No,
Why not?
we need the product.
Yeah, we need some way to like work with products. Right, so you see I'm just like disassembling like functions into their constituent pieces. Like everything ultimately is going to be either a combination of sums, multiplications, divisions, or powers. This is called an effective ring, if you're interested. Okay, we can't do this yet, so let's talk about the product rule. And the product rule, as you learned from high school, yeah, can anyone state it?
F prime times g plus g prime.
Yep, so it's the derivative of the first times the second plus the first times the derivative of the second. Okay, so now I'm going to use, oh, she's gone. Okay, I'm going to start using the more familiar notation. This, which is the one I prefer, right? This is pretty wordy. We can just write this as f prime g plus g prime f. Okay, I'm going to switch to this notation now, because I don't really care at this point to distinguish between the algebra and the geometry. Yes, sir?
Is it better notation to put the prime in front?
Like sometimes we're going to put this in front?
Yeah.
It doesn't matter.
Okay.
Right. But like you'll find that sometimes, we'll find things with like several types of notation, and it's for a reason. It's just hard to understand at this point why we need these two sort of ways of describing things. Well, first of all, it's because here, we only are using functions with one variable, yeah? So when I do this, you know that you derive with respect to x, right? But if this thing had 3 variables, then it's no longer well defined what it means to put a prime. Then we have to resort to this notation to say specifically I want you to take a derivative of this variable. Right, so we have both. The physicists even have a different notation. I don't know if you've ever seen this. Ever seen that? This is what the physicists use to denote this. Although their functions are throughout time, they indicate a dot to be a derivative throughout time. So you're going to see different notations for different reasons, culturally, and there are big cultural differences in notation, believe it or not. Yeah. Like the European style, the Asian style, the American style. Like in Australia, the natural numbers don't include 0. It infuriated me. I'm like, you're not allowed to change that definition. But they did. Okay. So we have this product rule. So let's do this example. Oh, proof of this. I'm going to be cruel. You do it. It's hard. So don't be too depressed if you can't get it. But it's in your ability. You maybe feel really satisfied for doing this. So here's an example. Let y equal 1 over x squared plus e to the x, and find y prime.
Bracket after exercise?
Oh, hard. Oh, I missed the D. It's hard. Okay, what do we got? Oh, you want a little bit more time? You guys want to try it?
Yeah.
You know, I just give you exercises so you're busy while I wipe down the boards. Right? This is a new strategy I have for keeping you guys quiet. Yeah, I know. Eh? All right, why don't you take a couple minutes? I can have a drink of coffee. I'll make one lap. Is that a question or a scratch? Is it a vote? Yeah. Did they do it? Okay.
They're just two different terms. It's just this term and that term. And it takes the derivative of this without this. And then it just decides that. Negative 1 over x squared.
No, you start with this other side. Okay, so you're trying to get something in between two. Okay. What you do is basically start with sign. Start with sign. You know,
That's another way to write it. Just have a negative 1. So you can just work from there. There's, but, yeah, don't worry about 1 over x.
okay.
I was just this so long. I just part of my words.
We don't really have any other bundles that are stuck to that.
E to the x is just
X squared is always going to be 1.
no, we had it one second. We had an instant go to my Greek 12 class because this is just such a stupid fucking thing. And I don't know, our calculator was like e to the x, and we're going to hold it to second. And he always says that. I should actually, have you gone back to the math class, or are you going to? What happened?
I just want to buy things.
Did you simplify it at all, or did you just leave it?
You can.
Let me see.
Oh, that's just going to.
They're all He didn't ask.
Yeah, we start here because try to do something
As long as you understand what you're doing.
Well,
If it's a simple
all
line,
the
it's
functions
fine.
satisfy this condition naturally. also like 3 negative.
Wait, why did you do that? Why did you switch it?
So you should be happy.
No. I can't, my writing's big and I didn't read in one line.
Oh.
You guys understand why it's there? I'm not doing it.
I can read my own writing.
Yeah. Okay, you guys get it?
First thing plus the bond.
Okay, I'm going to do it because like we got way like the second half of this lecture is actually way more complicated, and I want to get there because I have to teach you physics in like 40 minutes. I can totally do it. Okay, look, I'll show you. I'll write it out with some detail. I'll demonstrate that it's not too hard. So this means that y prime is equal to, and we just apply. So we have two pieces here, right? The 1 over x and the x squared plus e to the x. There's a multiple. You could have expanded it too, but that I think makes it a little bit more hard. Okay, so y prime is what? It's the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing.
Yeah.
So we're switching now to the notation you prefer. We can use this now. This is the one I prefer as well.
So, sorry, derivative of the first times
Whoops.
the second function plus the second function and the derivative of the second.
Indeed. Okay. What I recommend from now on, we stop using rationals, like we stop using this notation, and we stop doing this. Okay? Because both of these are hiding the fact that this is really this, one half, and this is really this. Right? So strive now to write everything as x to the power of something. It's going to make derivatives way easier. Okay. So the second thing I'm going to do here is just convert. So you get x to the minus 1 prime times x squared plus ex plus 1 over x. Whoops, I'm not even following my rules. This is going to be x to the minus 1, and then x squared plus e to the x prime. What's this going to be? This is going to be the minus 1 is going to come down. You're going to get minus x. Minus 1 is minus 2. Then you get x squared plus e to the x. Then you get x to the minus 1. And then here, this just, the derivative is just the individual derivatives over the sum. So that's 2x. And then e to the x.
Would we leave the negative exponents? Wouldn't we take it out of the negative?
Yeah, I'm not done yet. I still have to expand and simplify. Yeah, so at the end, you should remove the negative exponents. Although it doesn't really matter as long as your answer is equivalent to the correct answer. I'll accept all equivalent writings. Okay, so look, this is basically 1 over x squared. And this is an x squared. So if I combine them, it's x to the minus 2, x2, 2 and minus 2 makes 0. So the first thing here is a minus 1. And then you get a minus ex over x squared. I'm going to start putting them back because this is the simplifying phase. Plus, so this x over here, they will cancel. So you're left with a 2. And then you're going to get an ex over x. Okay? And then that's the thing. Well, then you can combine the 2 and the negative 1, but I'm not going to do it. Right? Again, you just need practice. Right? You're just mindlessly like applying the rules, and you just have to be careful. Okay, so what do I got? I'll give you an exercise that you can do. The solution's in the notes. That's for you. Okay, last rule. So what about stuff like this? Or actually, I have to make it a tad more complicated. How about this? Can you take the differential? Can you derive that? No. Exactly. That's yes. You're finally catching on to my tricks. Okay. So what rule do we need now? Quotient rule. Yeah. So now we're going to get the quotient rule. And it's like this. So this is f divided by g prime is equal to f prime g minus fg prime over g squared. Now, to prove this, I almost can prove this very elegantly, right? Because this is very close to using the product rule that we've already established on what? On this. Okay? But I don't have chain rule, and I need it. I'm future talking. We don't have. I have to develop the chain rule later. I know all of you love the chain rule. So I'm just going to leave this for the time being. Once I get chain rule, I'll come back and I'll give you a nice proof for this. But you can also do this algebraically, right? There is an algebraic one. There is a limit proof. You can find them anywhere on the internet.'re very boring. You hit the thing. Yeah.
My bad.
So if the video ever goes askew, you guys know who to talk to. Okay, these two guys right here. Yeah. Okay, work on this for a bit. And then we're going to do a quotient rule example. Okay, this is the last example we're going to do for rules. Okay, so here's a function. There are two ways to approach this. Either we're going to use both the product rule and the quotient rule at the same time. That's the first option. The second option is to expand this and then use the quotient rule. Which one do you want to do? I'll do one, you can do the other. I'll do the first one then, right? Because I want to demonstrate, like, there is, like, I can teach, basically, it's very trivial to show a computer how to take derivatives. I just tell the computer the rules and it can do it. It will reliably work it out. Thereby, this means that there's an algorithm. There's like a very unambiguous set of steps that you can follow to take a derivative. This is exactly the type of mathematics that you want, I feel. One where I can say, follow these steps, and you'll get the answer. The problem is these steps are difficult to execute. You need to practice doing it. Right? So this one, yes, it's the type of math that you like, but you have to practice. Right? Because as I'll demonstrate, these things can get a little bit crazy. Okay, so this means that y prime, and I'm going to give a lot of detail, but you should strive to eliminate as much detail as you can, to do these as quickly as possible. Because again, we're not testing your ability to take derivatives. Right? If I say, show me you can take the derivative of this, maybe then in that context, it's better to work things out. But if you're doing a derivative for a calculation for something else, then I don't care. Right? Just do it. Right? So you got to ask yourself, what are you being tested on in that question? And be careful. Okay, so there's a numerator and a denominator. Right? So I just look at this basically as something that's like an abstraction. It's just a box over a box. I just look at this and I say quotient rule. I'll worry about what's there in a bit. So the quotient rule says derivative of the top, that is to say the numerator, times the bottom minus the top times the derivative of the bottom over the bottom squared. Technically, this is already the derivative, right? If I fail to specify in an exam that you should simplify your answers, you could be a prick and be like, oh, here it is. You never said I had to simplify anything. In fact, there are some instances on your midterm that will explicitly say, don't simplify this. Right? If we ever wanted you to prove something like this, there is one question on your midterm for sure which says, do not simplify your answer. Right? Your answer in this box, don't simplify it. Right? So be sure to follow those instructions when given them. Okay, so what's next? So we got to take the derivative of this guy. we're going to take the derivative of this guy. So let's start with here. I'll write it. So this one is going to require a product rule. So hopefully I have a wide enough board. So in there, I'm going to write the product rule. This is going to be x, the derivative of x minus 1 times x squared minus 2x plus the first times the derivative of the second. Okay? And then that is multiplied by x to 4. And that gets subtracted. From that, I subtract x minus 1, x squared minus 2x, and then 4x cubed. And then all of this is over x8. Okay. So then what's incumbent now? So I see there's an 8 here. There's a cube there, and there's another 4 there. So the first thing that we can do is remove x cubed from the numerator and x cubed from the denominator, although we're technically dividing by 0. I'm not going to have time in class to solve everything now. But what I'd like you to do is go home and finish these things. It's good practice. Just to go in and fill in all the details. Right? I'd love to be able to sit here and write them all, but we'd have like 6-hour lectures. In any case, it's good practice for you to go home and fill them. So this is the answer, essentially. It's the unsimplified answer, so go and simplify it. Also, as an exercise, try it the other way. Expand the top first, and then do it. And then you should confirm that you're getting the same answer. Okay, so just the final thing I want to say about derivatives is that you can take a derivative twice. This is called the second derivative. Right? So for example, if I take x cubed and I do 2 things here. Right? This is basically just a statement saying do the derivative once and then do it again. So I can rewrite this like this. This is x cubed prime and all of that prime, which is equal to 3x squared prime, which is equal to 6x. Okay? So you can do it once, we can do it twice, we can do it 3 times. Later on in the course, we're going to do it n many times. We'll take the nth derivative. Funny enough, the first derivative measures rate of change, like how fast something is increasing. The second derivative measures the rate of change of that rate of change, which geometrically means we're measuring something called curvature. Right, so I'm going to give you now the physics interpretation of this. I'm not very good at physics, which is why I became a mathematician. So we're going to try to do this together. Is there anyone in here taking physics? Thank God. Okay, so no one is here to point out my mistakes. Okay, so I'm going to, that's the end of this part of the lecture. I'm going to write down the boards, have a chat with your friend. If you want, get up, shake off a bit. That's it.
Does this second derivative, like what you're about to do on top of it, like 2x is the rate of change on that?
Well, so I'm giving you, so today we talked about a bunch of algebraic rules for taking derivatives.
Right.
And so today, which is basically like, if I give you this and say take the derivative, you should be able to perform the mechanical operations to get it. The second half of this lecture is going to be us coming up with more geometric interpretations of what exactly we are doing. Because I can do this all mathematically. This is all like for fun, finding tangents, doing this. That's how we teach the mathematicians. So now I'm going to show you some physics. I'm show you how this relates.
What's the physical realize? It's 1, right?
All of this.
So what do you do when you take the derivative?
The tangent is telling you what the rate of change is.
So 1 plus 2 is 2, but 1 minus 1 is 0.
And its acceleration in this place. But if you think about what the slope is,
2 times 1 again is 2. Therefore that
is a rate of change.
So it's
How fast is my how fast am I going on?
Yes.
In terms of how fast I'm going. These are related. So that's what the slope measures.
You know, imagine just on 2. Imagine 2. How do you think it works? We know that it's next to the 0, right? When you bring down the 0 in front, the whole thing becomes 0. It doesn't matter that x to the power of 0 minus 1 is 1, right? You bring down the 0 down to the front, right? And that is equal to 0. I mean, like, the aesthetic is better. I don't know. It's either that or a picture of a dog or something.
I'll give you something harder.
It's a good quality periodic too.
It's so long, but ultimately easy.
No, you know, I fucking miss.
There's a difference between something being long and something being hard, right? These are just basic computations that you're doing that you have to take care of doing. It'll take a while, but it's not hard. That's the wrong word for it. Right? Cumbersome, maybe. Cumbersome. Yeah. Look, we're going to ask you to do hard things. Right? That's part of the deal. Right? Like you gotta, like this is the easy part of the course. By like orders of magnitude. Right? Because I can give you a set of rules to take derivatives. I cannot do the same thing for integrals. Integrals is like try this, you may fail. Then try this, you may fail. Then try this, you may fail. It's like building myself up, psyching out for the second part of the lecture.
Yeah, like the unblocked version of the website. And it was
Depends on the day when I can convince myself that you should have to take this or should not have to take this.
And then
Depends on the day. Depends on the wind's blowing. Well, sometimes I feel bad that all of you have to take calculus and maybe you don't really need it. But
I mean, the thing is, I talk to profs and they're like, when you do your research studies, you have a team that does your math for you. So like, you don't need to do your own math.
yeah, but this is why we're getting such bad science. Right? Like everyone's publishing science, all the math is wrong. Like it's now a better bet to assume that a psych paper is invalid. Greater than 1/2 chance that there's like a stats error that's so broken that it invalidates the whole thing. Oh, I love stats. Actually, I don't really like stats, but I like probability, which is different. There's like two sides of the same coin. We're going to be doing a little bit of stats and probability in this course. No, but no. But I'll show you. I'll show you that it's so. All the stuff you learn in statistics is just applied calculus. But the integral is, yeah. So is physics. You think if we apply calculus, it becomes easier?
Stats is easier.
You know how to apply stats. You don't know how to derive stats. Yeah, big difference. Okay, guys, you ready to learn physics in 40 minutes? Yeah, neither am I. But okay, so again, this is going to be just like a brief overview. This is not. It's just not possible that I'm going to be able to teach you all of this in the next 40 minutes. So I am ordering you to go home and read your book. Right? Read it a bit. Read the notes. Read any of the textbooks at your disposal. But this is going to be a totally insufficient explanation for you. I'm just going to try to give you like a just jumping off point for studying this. Okay. Rates of change. And don't groan at me because last semester I didn't do any of this. Like the 100% it was learning at home. Okay, rates of change. Okay, so calculus basically models Newtonian physics. And by Newtonian physics I mean the type of physics where I take a ball and I throw it and I want to figure out where it lands. Right? This is not quantum physics, which is like totally different. And it's kind of weird that like the type of mathematics that works on planets and the motion in this realm is totally different than the mathematics required to look at like the quantum realm. That's something in physics that they still haven't yet sort of been able to address. Right? They're looking for a unified field theory. But anyways, that's all string theory and who cares about that? Okay, so for instance, suppose roughly speaking, we want, or that we could measure a particle's position. And I say particle because it's weird in mathematics, because I have a point on a graph, but that point actually occupies no space. It's like infinitely small. Right? So we say particle to distinguish that, because the physicists really mean like something real that exists in the world, but tiny. Right? So tiny that we don't have to worry about the effect of its girth. Okay, so suppose, roughly speaking, we could measure a particle's position, and this position is called, we'll name it later. Then, right, the velocity is equal to how fast the position is changing. And acceleration measures how fast velocity is changing. Okay, this is the lecture in summary. Right? If you don't understand anything else about today's lecture, you need to understand three things. We're going to define displacement, velocity, and acceleration. You're going to have to be able to calculate those things. So you have two options for today. Follow along, understand, go home and study, or memorize 5 equations and be able to apply them. Right? That's the less good option, but it may work. So first we have to talk about displacement, which is a weird thing. Okay, so we need to somehow encode the particle's position, right? I'm saying we need to measure it, so somehow we need to represent it. We encode a particle's position by its displacement and not by distance traveled. So I live in St. Catharines. So if I drive back to St. Catharines and drive back to here, my displacement is 0. But I've driven an hour down the road and then an hour back, right? So we're not measuring distance traveled. We're measuring displacement. You pick a point, and then you say 6 seconds later, how far are you from that point? Because basically, this is all we care about. Right? If I want to measure your velocity and acceleration, I don't care that you're driving to St. Catharines or Buffalo or Australia, if that's possible one day. But, right, so we're going to abstract that away. We're saying the only thing that matters is how you're changing in position relative to some other position in time. So that's what the displacement is. So for example, and I'm not going to write it because there's a ton more writing in here. Okay, so here's an example. Suppose that's, so I'm going to say f of t, and I'm going to use t now instead of x to like just emphasize the fact that our independent variable is supposed to be measuring time. F of t is equal to position on the number line. All right, so here's the number line, r. Maybe 0 is here. And I can say maybe at f of 1, I'm here. So this is at 1 second, t equal 1 second. Maybe 3 seconds later, so f of 4, I'm here. So this would be t equal 4 seconds. So, question, what is my displacement from the first second to the 4th second? Oh, you can't answer this. Maybe this is at 2, and maybe this is at... Right, so this is all labeled terribly. I've confused you. Okay, so this means 1 second. This means at 4 seconds. This is the position, so let me call this position 3 and this position 14. Okay, this isn't time. This is, like I'm really saying that at 1 second we can, like there's an ant standing here. And then 4 seconds later, the ant has somehow walked to here. Right, so the ant can only walk back and forth along this number line. Like, let's leave it in one dimension for the time being. So from the 1st second to the 4th second, how much was I displaced by? 11 units, right? So the distance between here is 11. So, so the displacement is 11. Okay. Let's relabel this. I hate numbers, right? Because I've done something for exactly one example. I need to do it in general. So let's relabel. Okay, so here's my position at time t. I want to increment the clock by a little bit, right? I want to increment the clock by delta t, right? This means a change. They should have taught you this in high school. So I'm going to let the clock run a bit, and then we're going to find out that maybe f of t is here, t seconds later. Whoops. That should be t plus delta t. Okay. What's the displacement now? So displacement over t to delta t plus delta t is what? Yes, sir?
F of t plus delta t minus.
This minus this. It's the same thing you did before, right? Except now with I put an 11 here and a 7 here, but that's just basically what we're coming out of these functions. So the displacement here, which I'm going to call S, is equal to f of t minus f of t plus delta t. Oh, yes, it is. Okay. Well, again, displacement is much different than distance traveled. You can make a really long trip, and as long as it's a round trip, you haven't been displaced. Okay. So imagine now that I'm going to drop a ball. Here's the ground. The ball is at height h. I'm going to drop it from here. We're going to measure its displacement from its initial position. Its initial position is h meters in the air. Let's try now to draw a graph of the displacement, right? So what's this ball going to do? It's going to fall and then bounce maybe a little bit higher, then bounce a little bit lower. I wish there's a physicist in here because that person would know exactly how high the ball would bounce, but it decreases. Suffice it to say, the ball will come to rest. So if this is time and this is displacement, let's try to do a few of these things, right? So this is the initial position, okay? So I'm going to draw in here h, right? So at time 0, how much am I displaced by?
0.
Mm-hmm. Okay, so what's the next point of relevancy? Suppose then this ball hits the bottom. How much am I displaced by?
That's the maximum.
Which is what?
H.
H. Okay. So there should be a point here, right? So the ball, this line really shouldn't be straight. I don't know how it should be drawn. But anyways, that's more or less, it's a good approximation to it. So what happens, what can I say happens here in terms of what time? Like why is this a special instance in time?
Because at this time it touched the ground.
Yeah, so ball hits ground. What's going to happen next? How much? Should I go all the way back down? No. So I need to fall, I need to bounce almost back to the height. And then I hit the ground again. Then I bounce almost up to the height. And then I hit the ground. And then they'll taper off. These lines definitely aren't supposed to be straight. I think they're supposed to be curved a bit because this thing isn't going to do, I think the height goes quadratically down. But anyways, it's good enough approximation.
It shouldn't end up at the bottom.
Huh?
It shouldn't end up at the bottom.
Did I draw this backwards?
Shouldn't it end, isn't it going to be on the ground at the end?
Yes.
Yeah, so
The initial position was here.
Yes.
So its maximum displacement is when the ball's hitting the ground.
Yeah.
That's what I drew. Right, at the very end, when the ball is at rest, it is displaced by h from its initial position, which is up. Right, that's the confusing part. You can flip the whole thing if you want, but then you have to define this as being the maximum displacement, and you've kind of screwed with things a bit. Right, because we're asking how far have you been displaced from this time instance to some time instance before. So in terms of the ball, right, if you want to think it, like maybe you're uncomfortable. So another way that we could have described this, which is somehow a little bit more comfortable, is you're dropping a rock into the ocean. Right, because then I guess you consider the ocean as the top and the surface of the ocean as the top and it's going down somehow, but it's kind of equivalent. Okay, so I'm going to give you a definition of displacement. This is a definition. Yeah. So this is kind of a weird definition. So let S of t be displacement be the position of a particle along a real line. The displacement of the particle from t to t plus delta t is given by delta S. S is the thing that we're going to use to denote displacement. So the change in the displacement is given by t plus delta t minus f of t. Velocity. So again, velocity measures, if you think about it, how fast displacement is changing. Right, so if I run over here to check the time, but saunter back, my run to the clock, my displacement was changing more rapidly. Right? If you measured every second how much further along I was, you would see that that would be more rapid than my saunter back. This is the whole point of calculus. Calculus, tangents, are a measure of how fast something is changing. So in this context, if I start taking derivatives of the displacement, I'm going to get information back about how rapidly the displacement is changing. That's precisely the definition of a velocity. Okay, so how do I flesh this out? And again, you have homework. You have to go home and read this. So velocity, definition. Huh? I have missed the page. Maybe not. Okay, so I'll give you the definition first, then I'll give you an example. So velocity, and we're doing the easy one at the moment, the average velocity, is given by this, and I'll give you an example right afterwards. So the average velocity is how much have I been displaced over this time period? Right, so this is basically displacement over time, which is going to have units like, meters per second. And this is going to be equal to f of t plus delta t minus f of t. That's not surprising. This is what I just defined the displacement to be. And we're going to put this over delta t, the change in time. It should already be setting off bells in your mind. What is this familiar to? This looks fairly a lot like the definition of the derivative that we've been using. Okay, so in any case, so here's how you could conceptualize this. Okay. So it took Alice. Alice and Bob are the standard names we use in math, because you go from A to B. So no one can be offended, at least. Alice took 6 hours to drive somewhere 10 kilometers away. What is her average velocity? Right? You could do this without any calculus, right? I think you could do this in grade school, right? If I said, look, it took me 6 hours to drive somewhere 10 kilometers away, how fast was I driving on average? Yeah, we could plug it straight into the formula, but
We're given time, but we're given time in hours, so we convert it to seconds.
oh, you're not obligated to give time in seconds. It's just one example of time, right? As long as the unit is some measure of distance over some measure of time, it's fine.
Okay, so in calculus, it doesn't matter.
And nothing that it matters. You just have to make sure the units are the same when you combine two things, right? The units only become relevant when you're mixing units, right?
Sometimes in physics, they want it in meters per second.
Well, because they insist, make it seconds so we don't have to worry whenever we combine something that we're mixing units. Like they don't give you a meter per second on the highway. You're driving 100 kilometers per hour, right? So it depends on the context too. Okay, so in any case, if I drive, it takes me 6 hours to drive someone 10 kilometers away. That means I was driving, it took me 10 kilometers to drive somewhere 6 hours away. So I must have been driving at, you know what? 12. It must take me, I must have been driving at 2 kilometers per hour. Christ, no wonder it took me 6 hours to drive that far. Okay, so let me ask you some questions. Suppose I told you that my average velocity over this trip was 2 kilometers an hour. Does this mean does this mean I was just like driving through school zones, plowing kids as I was going through? Does this mean I never sped up or slowed down? No. This is just the average velocity. On average, you were traveling this much, right? This doesn't imply that you didn't stop or speed up or slow down, right? So this is just telling you an average over some time interval. Now, we would like to be able to answer the question, how fast was Alice traveling, or what was Alice's velocity 3 hours into the trip, right? If you're driving your car, at any given moment, you could look down at your speedometer, and hopefully you're driving the speed limit, right? So you're driving exactly 100 kilometers an hour down the 400 highways, I imagine. But at any instance, you can look down and see your instantaneous velocity in that instance, which is different than velocity. Your instantaneous velocity is your average velocity over an infinitely small time interval, really. Right? That's the calculus interpretation of it. So here's average velocity. You know things are going bad when I have to use the forbidden board, but let's go. I have to now give you the definition of instantaneous velocity. So here's the definition of instantaneous velocity. Right? This is the average velocity with delta t is equal to 0. Okay? What is this? This is very interesting. If I set delta t is equal to 0, what do we get? We get the velocity, the instantaneous one at time t, is going to be the limit. Look, I can't divide by delta t. I can't make delta t 0. I'm not allowed to divide by 0. Thankfully, we've spent all of this time developing a tool that which is going to allow us to take numbers arbitrarily close to other numbers. So I'm not going to divide by 0. I'm going to divide by delta t and take delta t to 0, which is something that's going to end up working out, which is why we need it. Okay, so we're going to do this. The interpretation of this being, this is my average velocity over an infinitely small time interval. What is this? This is the first principle's definition of what? You see how these things are related? These things are intrinsically related. Like Newtonian physics is almost like a natural implementation of calculus. It's like naturally occurring calculus. So this example up here, what is Alice's velocity? What is Alice's velocity at, give me a time, 2 hours. All right, so what do we need here? How can we answer this question? Yes, sir. It's not v of 2. Well, oh, sorry. Yeah, it's this v of 2. Okay, so let's start from there, right? Because that's not bad. We need v of 2, which means we need, Sorry, this should be average velocity. V of 2 is the derivative of the average velocity by t. And then after we finish that, then we put in 2. So be careful, right? When I'm telling you to find the derivative at a certain time, you have to evaluate afterwards. What happens if you put the number in first and then derive? We just learned today, what's the derivative of a number? 0. So if I have a function and I evaluate it, it becomes a number. And then its derivative is 0. Right? So that's not how you do it. So we have to take the derivative first and then evaluate it. Okay, so what is the derivative of the average velocity? No, sorry. Oh, I really have screwed this up. I have to tell you what her displacement is. Okay, so I'm just going to make something up. So it's no longer about Alice. And she's really into herself. I think we got to go talk with Bob. All right, so Bob's displacement is given by, and I'm just going to make something up, right? And then we're going to ask ourselves what kind of interpretation this is. Okay, I just made that up, came out of my head. It's a parabola. So I'm telling you Bob's displacement is given by, at time t, he is going to be t squared plus 3 meters displaced. So now then, what is the average velocity? Well, it's, oh my God, this is all wrong. What am I doing? I told you I was bad at physics. Yeah. Hold on. This should be not the velocity. I knew something was wrong. This should be the displacement. Yeah, sorry. Because I was supposed to make the point that like this, a way to interpret this is the change in S over the change in t. And the notation here is very similar to the notation here, deliberately, yeah.
So you wrote acceleration before.
I did write acceleration before, yeah. So, yeah, that's the spoiler for the next thing, right? It's the change in the position over time. Gives you the velocity. Okay, so, sorry guys. That should be S of t. So now I'll just complete it. So, okay, well, I apologize for that mistake, because I know it's harmful. But in any case, here's the displacement. Here's the definition of the velocity now written correctly. So can anyone tell me what the derivative of this is with respect to t? 2t. Okay, so this is going to be 2t. And then we have to evaluate this function at 2. Right, so don't get confused. This isn't multiplication. I know sometimes things can get confusing, but so be it. So if I put 2 into here, you get 4. And it's going to be 4 meters per second squared. Okay? The way to interpret that squared on the bottom is the velocity is saying, in this instance, at every second, the velocity will increase by 4 meters per second. So if I'm at rest and I count 1 second, at 1 second I should be traveling at 4 meters per second. At the second I should be traveling at 8 meters per second. And then 12, and then 16. Right, so that's how you interpret the velocity, right? Yes, miss?
Oh, sorry, so we plug 2 in.
You have to do the derivative first,
Right.
and then you get a function, and then you can evaluate it. Because if I put the 2 into here first, this would become a constant, and its derivative would be 0 every time.
Okay, no, because I just got a little bit confused because you gave us the function, but you didn't give us, like, the time. You just...
Well, you can tell me what the velocity is at arbitrary t. It shouldn't make it... t's better than 6. Right? T tells me what the velocity is at any of the times. That's a lot more flexible than telling me where it is at 3. Right? Yes, sir.
So at the end there, it's going to be 2t of t?
Yeah, of t. This is like...
multiplying.
If you, yeah, this is not multiplying.
Yeah.
What I want to write is this, but I'm afraid it's going to freak you out. Is that better? Yeah. Okay, I'll use that then. Fine. But don't yell at me now. Don't let that confuse you, right? So this, I'm going to use this now as a notation to say that t equals 2 should be put into whatever's in brackets. I'll use it now, if you prefer. I do prefer it, but I was told not to use it. Okay. How much time do we got now to teach you acceleration? I can do it in 10 minutes. I can do it. I can do it. Again, you're going to have to go and read a chapter on this. Like, it is kind of confusing. It's sort of shoehorned into the course. The physicists really insist that we show you this.
So is this you'll definitely see something?
Yes. Yeah. You for sure, we're going to ask you a question like, so for this topic, it's mostly like, do you know what the definition of average velocity is? We're going to ask you a question like, calculate the average velocity of this. So as long as you remember the terms, the three terms, displacement, velocity, and acceleration, and I guess average velocity and instantaneous velocity, you should be able to do it. Right? This is just not, we're obligated to show you this because of the physics department. This is why it's in the curriculum. I'd rather teach you probability. Okay, okay, velocity, rates of change, blah, blah, blah. So read the notes. They're a lot more comprehensive than what I did on the board. So I'm just going to finally mention acceleration. So let Vt give the instantaneous velocity. Then the acceleration of t is equal to the change in velocity instantaneously, which actually is going to be the, let me write it this way, the second derivative of s with respect to time. So this gives acceleration. This is acceleration. So example. So for that guy I just invented for Bob. So Bob was moving like this. This means that his velocity was given by this. Whoops. 2t meters per second, which means that the acceleration is just the next derivative of this, which is 2 meters per second cubed. Right? Meters per second per second per second. So what can we conclude from this? Well, Bob seems to be in some type of like physics-defying spaceship. Right? He's never returning. He's just heading, like this is basically a rocket ship that I fired into the universe. Right? Because this never comes back. Right? You put in bigger t, he's getting farther and farther away from us. In fact, at every second, his speed is increasing by 2 meters per second. He's infinitely speeding up, which we can get from this. This basically is against the laws of physics. Nothing can have a constant acceleration for forever, right? Maybe in the vacuum of space. I don't know, I've never been. Heard it's lovely at this time of year. Bring your own oxygen. Okay, so, okay, if you don't understand physics, it's fine, neither do I. Again, I'm going to emphasize, displacement, velocity, acceleration, and velocity branches into average velocity and instantaneous velocity. Commit them to memory. Okay, last question for today. I'm just going to draw you, I'm going to erase this example. Scream at me your questions if you want. Okay, so here's your last exercise. Where did I put it? Here. Okay. So be careful. What I'm going to give you right now, this is going to be, okay, so interpret this velocity graph. Okay, so what I'm going to draw you here is a diagram of the velocity of a particle. Velocity. This is over time. So this is going to tell you about the velocity, instantaneous velocity at that time. The velocity does this, then this, then this. Then it does this. Then it flatlines. And then it does this, right? So you got some obvious regions to investigate. And namely, I want you to label these. I want you to label where the graph is going, where the particle moves forward, where the particle moves backward. Well, there's one final thing that I had to mention. Velocity has signage, right? So if you're going forward, which you just sort of define, that's positive velocity. Negative velocity is moving backwards. Sometimes we don't care about the sign, like moving forward or backwards. So we say that the speed of an object is just the absolute velocity of its, absolute value of its velocity. So if you're traveling 10 meters per second backwards or 10 meters per second forwards, you're nonetheless traveling at the same speed. Okay, so forward, backward, Where is the particle moving the fastest? Where is it speeding up? Right, that is to say, where is its acceleration greater than 0? Where is it slowing down? That is where the acceleration is less than 0. And then where is it steady? Okay, if you want more explanation, come visit me in my office hour, or surely you guys know people who studied physics. They can walk you through it. This is the basic physics. Okay, good luck. Goodbye. Yes, miss. Oh, probably not. No, today.